Hello students, very good morning to all. This is welcome back to my channel. This is Dr. Nagina Parveen, Associate Professor in the Department of Electronics and Communication Engineering, SR University. The topic of the day is analog filter designing. So analog filter we can design using by two designing methods. One is a Butterworth filter, second one is a Chebyshev filter. Now today's topic we will learn about how to design an analog filter using the Butterworth filter. Now the designing steps of the Butterworth filter. Firstly, we have 5 designing steps. The designing steps included with so first designing of the filter using the Butterworth designing steps. So first step is, in last class we have discussed about the how to derive the expression. So we have derived the expression for finding the order of the filter as well as the cutoff frequency. Now first step 1 is find the order of the filter using the formulas as n always greater than or equals to log of base 10 square root of cutoff, that is stop band attenuation divided by 10 power 0.1 pass band attenuation minus 1 divided by log of base 10 omega s by omega p, or we can use log of base 10 as lambda by epsilon divided by log of base 10 omega s by omega p. Now we have lambda is equals to square root of 10 power 0.1 alpha s minus 1 and epsilon is equal to 10 power 0.1 alpha p minus 1. Now using, suppose if the given characteristics are, this is a frequency characteristics of the low pass filter. Suppose it is given 1 and it is our mode of h of omega and this is omega. So we have this as the passband attenuation, yet we have passband frequency. Now here we have stop band attenuation. So remember always passband frequency, passband attenuation and stop band attenuations always should be dBs. If the given specification alpha b passband attenuation and stop band attenuation as in terms of dBs, you have to consider the first formula. Now suppose if in the characteristics, if it is given it is 0.9 and it is 0.1. Now from this specification we have to equate this to square root of 1 by 1 plus epsilon square and this value to square root of 1 by 1 plus lambda square. If you are equating the 0.9 as the square root of 1 by 1 plus epsilon square, then you will get it as epsilon value and next value you will get a lambda. So therefore you have to use n greater than or equals to log of base 10 lambda by epsilon divided by, here you have passband frequency and stop band frequency. Therefore passband frequency, that is stop band frequency by passband frequency you have to consider. Now these are the formulas from the given specification you have to consider. Now step number 2. Step number 2 is finding, suppose from the step number 1 if you got n is greater than or equals to 2.2. So you have a fractional number. The filters cannot be in terms of a fractional numbers. So that the step number 2 is rounding step number 1, that is rounding of n. So round the n value to next highest integer, that is a step number 2. So if I got the highest value more than, that is 2.2, is n is equal to 3. Suppose the n value if I got is greater than or equal to 0.2, then the highest integer is n is equal to. In the formula itself we have n greater than or equals to. If it is integer it will be equal. If it is fractional value it will be greater. Then step number 3. So step number 3 is regarding to the finding the normalized transfer function. That is, in step number 3, we will consider the cutoff frequency as exactly 1 radians per second. So therefore, we have to find out the h of s. For h of s, it is 1 by the polynomial 1 by d of s. So these polynomials is nothing but, suppose if n is equal to 3, then we have how many poles of the system? 3 poles we have. So 3 poles we can write it down as s minus first pole, s minus second pole, and s minus third pole. If it is a kth order filter, then I have s minus sk, where sk, the kth pole, we can determine using the cutoff frequency into e power j 5k, where k depends on starting from 1 up to so on, ending with the order of the filter. Now we have, if so, normalized frequency, normalized transfer function omega c is equal to 1 radians per second. So therefore sk is equal to e power j into 5k, where 5k finding the phase, that is 90 degrees plus 2k minus 1 into pi by 2n. K is equal to starting from 1, 2, 3 up to so on, the order of the filter. If k is equal to 1, then if I substitute, that is, suppose if order of the filter is, if order is equals to 1, from step number 1 and 2, if you got the order of the filter, that is 1, then the k value is equals to 1. If I substitute in the equation, then phi 1 is equals to pi by 2 plus 2 into 1 minus 1 divided by pi by 2 into 1. Therefore, I will get pi by 2 plus pi by 2. What is the phase here? Phase is equal to pi. If phase is equal to pi, if phi 1 is equal to pi, then s1 is equal to e power j phi 1 is equal to e power j pi. We know from Euler's formula, e power j theta is equal to cos theta plus j sin theta. Now I can write theta here is pi, cos pi plus j sin pi. So cos pi value is minus 1 and sin pi value is 0. Therefore s1 is equal to minus 1. If s1 is equal to minus 1, then the polynomial d of s is equal to s minus s1, only one pole, because the order is only 1. So I have s minus of minus 1 is equal to s plus 1. If d of s polynomial is s plus 1, then the normalized transfer function is equal to 1 by polynomial, that is equals to 1 by s plus 1. Suppose if k is equal to 2, that is order of the filter is equals to 2, then k value is equals to 1 comma 2. If k is equal to 1, then phi 1 is equal to pi by 2 plus 2 into k value is 1 minus 1 divided by 2 into what is order of the filter? 2 into pi. Therefore, pi by 2 plus pi by 4 is equal to 3 pi by 4. If k is equal to 1, then if k is equals to 2, then we have phi 2 is equals to pi by 2 plus 2 into 2 4 minus 1 pi by 4 is equal to pi by 2 plus 3 pi by 4 is equal to 5 pi by 4. Then s1 is equal to e power j 3 pi by 4 is equal to cos 3 pi by 4 plus j sin 3 pi by 4. Then if s2 is equal to e power j 5 pi by 4, then cos 5 pi by 4 plus j sin 5 pi by 4. Then cos pi by 4 and 5 pi by 4 you have to substitute. Then we have the cos pi by 4 value is minus 1 by root 2, that is 0.707, and sin 3 pi by 4 is again 0.707. Again, cos 5 pi by 4 value is minus 0.707, and sin 5 pi by 4 value is equals to minus 0.707. So therefore, if you are having n value is equals to 2, n value is equals to 2, then we have two k values. Therefore, we have two poles of the system. Now, the polynomial that is d of s is s minus s1 into s minus s2. If I substitute s1 value and s2 value, the final polynomial I will get it as s square plus root 2 s plus 1. Therefore, the h of s is s square plus root 2 s plus 1. Similarly, if n is equal to 3, then k will be 1, 2, 3. If I substitute in the same procedure, then the polynomial I will get it as s plus 1 into s square plus s plus 1. If n is equal to 4, then we have 4 k values. Then each and every term you have to substitute the k value and get the equation. Then you will have two equations depending upon s square plus square root of s square plus, so the coefficient is 0.7653s plus 1. Here s square plus 1.8477 s plus 1. So we have, by considering all these values as into account, we have the table called Butterworth filter table, which gives the details about Butterworth filter table, which tell us about what is the polynomial for the given order of the filter. So we have n is equal to 1, 2, 4, 7. Then the polynomial for n is equals to 1, we got s plus 1. For n is equal to 2, we have already substituted and get our formula as s square plus root 2s plus 1. If n is equal to 3, also we have derived s plus 1 into s square plus s plus 1. If n is equal to 4, we have s square plus 0.7653s plus 1 into s square plus 1.8477 s plus 1. So here just to remember, if n is equal to order of the filter is 4, then you will have 4 poles of the system. So just to remember this coefficient and this coefficient. Then if n is equal to 5, s plus 1 into s square plus 0.6180 plus 1 into s square plus 1.61803 s plus 1. See, if it is 5, if it is 1 s plus 1, if it is 3 s plus 1 multiply, if it is 5 s plus 1 multiply, if it is 7 also s plus 1 multiply. Then here also you have to remember same coefficient, one is 0 and second one is 1.61803. Similarly, if n is equal to 6, then the polynomial d of s is as s square. So 6 poles we have, 1.93185 s plus 1 into one more s square term, s square plus root 2 s plus 1 into s square plus 0.57764 s plus 1. Similarly, if n is equal to 7, we have 7 poles, that is s plus 1 multiplied with s square plus 0.180194s plus 1 into s square plus 1.247s plus 1 into s square plus 0.44 s plus 1. Now this is the Butterworth filter table, so that we can check our polynomial directly using this table. Now remember this table for future reference. Now we have derived for 3 steps. Now fourth step is, so in general the cutoff frequency will not be equals to 1, that is normalized if it is equals to 1. But to find out the unnormalized cutoff frequency, thereby unnormalized transfer function, the cutoff frequency formula we have is in terms of stop band frequency, or we find out we can using the pass band frequency. If it is a stop band frequency, then 0.1 into stop band attenuation whole power 1 by 2n, or if it is a pass band frequency, then we have pass band attenuation, or we can find out this cutoff frequency in terms of lambda and epsilon also. So lambda power 1 by n, or we can find out the epsilon power 1 by 2n. Now after finding the cutoff frequency, we have to find out the unnormalized transfer function. So this is overall analog transfer function, analog filter transfer function. To find out this overall analog filter transfer function, then finding the analog filter transfer function as, so from step number 3 we already got the h of s. So h of s from step number 3, and from step number 4 we got the cutoff frequency. So remember the cutoff frequency, whether you are substituting the passband frequency, passband attenuation, or with the stop band frequency, stop band attenuation, the cutoff frequency we have to consider as highest one. So if you are finding the cutoff frequency using a passband and stop band, passband frequency, passband attenuation, suppose if you are getting the 12.44 radians per seconds units. So if you are finding the using the stop band attenuation and stop band frequency, if it is 8.944, okay, so in between these two the highest value is 12. So highest omega, that is cutoff frequency, you have to consider as 12.44 radians per second. This is for assumption. So make sure that the cutoff frequency always will be in terms of passband frequency and stop band frequency. So here we have a passband frequency, here we have a stop band frequency, and this cutoff frequency you have to consider as a highest. This is a cutoff frequency where the signal is having the gain is exactly half of the maximum gain. Then the last step is finding the unnormalized transfer function, that is overall analog filter. So the unnormalized transfer function is equal to, so from step number 3, wherever you have h of s has to be replaced by s by omega c from step number 3. In step number 3, so s has to be replaced by s by omega c. Now simplify this expression after substituting the s by omega c, and write in terms of the coefficient, always write the coefficient of s square term as 1. So that is our final low pass filter designing. If it is a high pass filter, if you are designing the high pass filter, then first step finding the n value, then rounding the n value, that is same. Then third step, which is finding the unnormalized transfer function, it is also same. Then finding the cutoff frequency using the formulas, this is also same. So these 4 steps are same whether you are designing the low pass filter or you are designing the high pass filter. And the last step, in terms of low pass filter, we have substituted for low pass filter h of s by omega c. So this is the ideal characteristics of the low pass filter. But ideal characteristics of the high pass filter is opposite. So we can see all high frequencies it will mellow, all low frequency it is stop. That is, this is stop band and this is a pass band. So therefore, and the last step is, wherever you have S in step number 3, replace S by omega C by S and simplify the expression. So there you finally design your high pass filter. So these are the designing steps for designing the high pass filter and low pass filter using the Butterworth filter. Now in next class we will take one more design process. So by using the same design process, we will see how to make a characteristics. So suppose if an example if I consider, so this example we will solve in the next class. So 0.9, then magnitude of h of j omega less than or equals to 1 for 0 less than or equal to omega less than or equal to 0.4 pi, and the magnitude is less than or equals to 0.2 for 0.5 pi less than or equal to omega less than or equals to pi. So these are the given specifications, right? So from the given specification, firstly we have to draw the characteristics. So these characteristics, x-axis is omega and y-axis is the magnitude of the h of j omega, right? So if you are identifying the maximum is 1, so we know we have maximum and omega is equal to 0. At omega is equal to 0, the maximum is 1. And we have a limit 0 to pi. In between 0 to pi, somewhere we have 0.4 and 0.5 pi. Now 0.9, next limit it has given, and next limit it is given as 0.2. Now we know the characteristics of the low pass filter as this is the characteristics. Now this 0.9, if I touching the characteristics, where it is touching, so there we have one frequency, and this 0.2 where it is touching, that is we have one more frequency. So this 0.9, that is y-axis, where is touching the curve, that particular frequency we can call it as passband frequency. Now at 0.9, the frequency is 0.4 pi. That is our passband edge frequency. Now next range is 0.2. At 0.2 we have this pi is maximum, but between maximum we have one more, that is 0.5 pi. So this 0.5 radians per second is stop band frequency. So we have passband frequency and stop band frequency, and always remember, if it is alpha p directly, that is 20 dB is given, if alpha s, that is 30 dB is given, then you have to consider it as first formula for finding the n value. Now here we have given a characteristics specification. From this specification we have to equate 1 by 1 plus epsilon square as 0.9, and 0.2 has to be equated as square root of 1 by 1 plus epsilon lambda square. So from this you will get epsilon and lambda, you got omega p and omega s. Therefore you have to use those formulas to solve and to get your low pass filter or high pass filter. So next class we will discuss about how to use those formulas to designing of these low pass filter or high pass filter. So for these specifications we will consider, so design the low pass analog low pass filter for this given specifications. So that we will discuss in next class. Thank you so much for listening this video.